This is Kevin Cole at the University of Nebraska. The topic is thermodynamics, and the example is pressure and boiling point. And we're going to explore the effect of elevation on the boiling point of water. And the way we're going to do that is by looking at, to start, a PT curve that shows some behaviors of water. So here's pressure versus temperature. And this plot shows the critical point here. It shows the triple point here. And the different phases present, well, to the left, in this region we have solid. In this region we have liquid. Let me extend this one bar line a little bit, thinking about along that line. Below the critical temperature, we have vapor, and above the critical temperature we have gas. And we're interested in the liquid vapor portion of this curve, and this line is called the saturation line. All right, so here we have, we're told that at 1 atmosphere, 1.01 bar, water boils at 100 C. Suppose we're at 10,000 feet and the air pressure is lower, now 0.74 bar. What's the new boiling point of water at this elevation? So the PT diagram tells us something about the fact that the boiling temperature descends when the pressure descends. To get detailed information, we need the saturated water table or pressure table. Let's take a look at that table. Here is properties of saturated water pressure table. We've got values for pressure down this side, and we have values for temperature next to it. So these two columns show us the detailed information on the saturated line from the other curve. Let's go back. Now what we're going to do is to transfer some of this information, and we're looking for what's happening at 0.74 bars. We need to look in the table and find values in that area. Let's go back to the other table here. And here we have 0.7 bar and 0.8 bar, and then we have a couple of temperatures there. So I'm going to transfer this information to the other table. And at 0.7 bar, it's 89.95 centigrade, and at 0.8 bar, it's 93.5 centigrade. So let's go back. All right, so we've got values at 0.70 bar. I'm going to leave a space, or I'll put in the missing value that we're looking for at 0.74, and the other value from the table is 0.80. And at 0.0 bar, the temperature is 89.95, and at 0.8 bar, the value is 93.5. And the value we're looking for is here. So I could say put an unknown t. Now before I stop looking at that table, I want to remind you that you need to carefully say which table. And that usually includes where the source, say a book, the title, the table, and the page number. So in this case, let's go back and peek over the other table. In this case, I want to say page 722, table A3. And this is an example, a typical table. So page 722, table A3, from this source. And the reason you do that is so that a future you can find it, or so your instructor can understand what you've done, or your boss can understand what you've done. It's very important to state clearly where you get your values. All right, we're going to look for this temperature, and we're going to do that by interpolation. We're going to interpolate. And here's how that's done. I think about interpolation as a ratio of distances. This distance compared to that distance. So we'll say ratio of distances. And let's set that up. So the first distance is the short one. I'm going to put in this short distance here, 0.74 minus 0.7, and that's in bar. I'm going to divide by the longer distance, 0.8 minus 0.7, and that's also in bar. I'm going to set that equal to a ratio of distances here. The short distance is going to be t minus 89.95 divided by this distance, which is 93.5 minus 89.95. Now both of these distances are in centigrade, I guess, excuse me. Centigrade. So the units cancel out. So it's dimensionless ratios. And now we can crunch some numbers. This is a pure number, and this is 0.4. And on this side we have upstairs t minus 89.95, and downstairs I can find a value for this distance. It is 3.55. And we can rearrange this further in solving for t. Let me scroll up a little bit. Now I like to do algebra when I solve for things. So I'm going to get, let me cross multiply and say 0.4 times 3.55 is equal to, the right hand side now is t minus 89.95. I can move the 89 over here and rearrange it. I can get t is equal to 0.4 times 3.55 plus 89.95. Almost done. And then I can simply evaluate that, and I'll get the temperature is 91.37 C. Now a quick check, that's the answer. But a quick check is the value that you get in between the values from the table. And 91 is in between 93 and 89, so yes, that checks. All right, what are the consequences of a lower boiling point? What's the impact on your life? Well, if you're at an elevation where there's a 91 degree centigrade boiling point instead of 100 centigrade, it takes longer to cook things. And you might have to use some high altitude directions to know how to get your altitude, to know how to get your food to come out the way you expect at lower elevations. Or you might want to consider using a pressure cooker to push the boiling point back up again. All right, let me recap. We were asked to study what happens when the air pressure is lower and find the new boiling point. And we used a PT curve. And the PT curve, because of the slope of the saturation line, when the pressure goes down, the boiling point goes down. So that slope of that line tells us that. We used a table, and the particular table we used was the pressure table, but it's always important to say exactly where you got your table so that your boss or a future you can find out those values. We used interpolation to work between a couple of table values to find the value we were seeking. And we found that the boiling point went down more than 8 degrees. And then finally, if you visit the mountains, if you bring along a pressure cooker, all will be well.